After completing this lesson, the student shall be able to explain the designs and operations of automatic sprinkler and standpipe systems and to calculate the pump discharge pressure necessary to supply automatic sprinkler and standpipe systems. After completing this lesson, the student shall be able to describe the design of the common types of sprinkler systems, describe the components of automatic sprinkler systems, and differentiate among the varying types of standpipes. Also, the student will be able to calculate pressure and loss and pump discharge pressure for standpipe systems. Right now we're going to go over learning objectives 1 and 2. Even though we reviewed all of them, we're going to go over 1 and 2. Sprinkler systems are designed to provide automatic fire suppression using a system of underground and overhead piping. Include one or more automatic supplies and include network of specially sized piping installed in building, structure, or area to which actual sprinklers are attached. They typically are activated by heat from fire and include device for actuating alarm when a system is operating. To correctly utilize sprinkler systems, firefighters and pump operators must have a working understanding of every facet of these systems. The earliest sprinkler systems were crude and unreliable. Modern sprinkler systems are much more effective and reliable. 3 main reasons motivate building owners to invest in and install automatic sprinklers. The 3 main reasons are code requirements, insurance purposes, and general fire protection. Also, the reasons for mandating sprinklers in buildings arise from a need to protect community and protect occupants in individual buildings. Laws requiring sprinklers may be based on a combination of building occupancy, construction types, and size. Most insurance companies offer significantly reduced fire insurance rates on sprinklered properties. The common types of sprinkler systems and their designs. Fire professionals will encounter 4 basic types of sprinkler systems: a wet pipe system, dry pipe system, a deluge system, and a pre-action system. Common types of sprinkler systems and their designs. For any sprinkler system to function properly, it must be designed correctly, installed correctly, and of course maintained correctly. Inadequately designed systems cannot be expected to control fires. There are 2 basic factors that determine the appropriate type of system to design and install. A is the type of building and B is the type of occupancy to be protected. Other variables include types of sprinkler heads to be used, spacing between sprinklers, types and sizes of pipe to be used, types of pipe hangers that will support system, types of valves, alarms, drains, and other systems, and other components to be used. NFPA 13 provides for the design of most sprinkler systems for most types of occupancies. Other standards may be consulted concerning exceptions to NFPA 13. When using NFPA 13 to design a sprinkler system, A designer begins by determining the occupancy hazard classification to be protected. NFPA 13 divides occupancies among three classifications: a light hazard, ordinary hazard, and extra hazard. A light hazard will probably have a low rate of heat release if they catch fire because the quantity of combustible contents is low. This may include churches, hospitals, offices, and apartments. An ordinary hazard is divided into two subclasses depending on the amount and configuration of combustibles as they contain. Ordinary hazard group 1 includes occupancies where combustibles do not exceed 8 feet or 2.4 meters in height. And ordinary hazard group 2 includes occupancy where combustibles do not exceed 12 feet or 3.7 meters in height. Ordinary hazard group 1 includes bakeries, canneries, and electronic plants. Ordinary hazard 2 includes cereal mills, confectionery products manufacturing, printing processes, and tire manufacturing. This car stereo manufacturing plant would be an ordinary hazard group 1 occupancy. Now, when talking about extra hazards, we're discussing hazards where severe fires can be anticipated. It's subdivided into two groups. Extra hazard group 1 occupancies include particle board manufacturing, sawmills, textile packaging. Extra hazard group 2 includes occupancies with flammable liquid spraying, varnish dipping, and low coat operations. Occupancies that fall primarily within one class may also have characteristics of another class. Common types of sprinkler systems and their designs. You have a pipe schedule method and a hydraulic calculation method. These two methods of system design are used to ensure piping is properly designed and sized. A pipe schedule method specifies the pipe size that must be used to supply a given number of sprinklers. It's typically less expensive and requires a larger pipe. Very few systems are designed with this method. The pipe schedule method specifies pipe size that must be used to supply a given number of sprinklers. It's typically less expensive, requires a larger pipe, and very few systems are designed with this method. Hydraulic calculation method uses scientific formulas to calculate pressure loss of water flowing through sprinkler pipe. It ensures a system will meet minimum discharge requirements and permits the use of smaller pipe. The computer programs do most of the calculations. Wet pipe sprinkler system are the most common reliable type of sprinkler system. It controls fires with the minimum number of sprinklers opening. The entire piping system is always filled with water, allowing water to immediately discharge from individual sprinklers, typically installed in locations where they will not be subject to freezing temperatures, and they are of limited size so that they may be installed in areas subject to freezing if they are freeze protected. Wet pipe sprinkler systems contain an alarm check valve or a water flow indicator in their risers. It senses movement of water in the system and triggers an alarm to sound. An alarm may sound only locally or may broadcast to monitoring center so that a fire department can be dispatched. These are common types of sprinkler systems and their designs. You see here the components of a wet pipe sprinkler system. You see the standpipes, and you see the local alarm interior, and you see the main drain, and you see the riser, the fire department connection, etc. You see the operational sequence for wet pipe sprinklers. This heat from fire causes sprinkler's heat actuating plug to drop down from the frame. Water and piping immediately discharges from the open sprinkler. As water begins to flow through the system, the alarm check valve on the water supplyzer activates. The alarm is transmitted to the supervising or fire department. If needed, the volume and presence of water in the system is boosted via the department pumper through the fire department connection. The dry pipe sprinkler system involves air under pressure that replaces water in pipes above the sprinkler valve in the riser. Commonly used in buildings but not sufficiently heated to keep water in sprinkler pipes from freezing. The riser and dry pipe valve must be in heated portions of the structure. Here you see a diagram of common types of sprinkler systems and their designs. So you see the dry pipe valve uses air under pressure to hold back water. And you also see the various gauges. You see the air pressure gauge, the riser, you see the indicator going to the alarm, the main valve and drain, and the main water control drive, etc. The dry pipe sprinkler system forces compressed air and may be obtained from one or two sources: the air compressor and tank arrangement, and the facility-wide compressed air system. Either is equipped with electric or hydraulic or water alarm signaling equipment. The operational sequence for a dry pipe sprinkler means that heat from the fire causes heat actuating plug in the sprinkler to drop from the frame. Pressurized air in the piping begins to flow through the open sprinkler. After a slight drop in air pressure, quick opening device, if present, activates to accelerate the removal of air from the piping. Once the air pressure is reduced sufficiently, dry pipe valve trips open again and an interior clapper is held in open position by the operational sequence for the dry pipe sprinkler means that water enters intermediate chamber of a dry pipe valve, automatically forcing automatic drip valve closed, and begins the flow of water through the alarm signaling equipment. Water then flows through the entire piping system and is discharged through the open sprinkler. A deluge sprinkler system means that piping controls no water before the activation of the deluge valve, but that all sprinklers have open heads with no fusible links. When a valve is tripped and water enters the system, water will discharge through the sprinklers simultaneously. Sprinklers do not function as a detection device. Sprinklers do not function as a detection device, and the valve is activated by heat, smoke, or flame detectors installed in the same area as sprinklers. A deluge sprinkler system is installed in situations that require quick application of a large volume of water. It's normally not used to protect extra hazard occupancies. It may be equipped with a foam proportional discharge capability. It frequently is used to protect equipment at large electrical substations. They are almost always supplied by fire pumps. These are common types of sprinkler systems and their designs. And you can see the open sprinklers, the water motor alarm, the water pressure alarm switch, the manual valve, the electrical manual control stations. So this is all pretty self-explanatory. If you just take a few minutes to review it, it shouldn't be very hard for you to get a grasp on. Operational sequence for deluge sprinkler system means that direct senses provide fire condition or an individual working in an area that discovers fire. Fire detection system sends a signal to the deluge valve, causing the valve to open, or an individual who discovers the fire manually trips this kind of device. As water enters deluge valve and piping, water flow indicator alarms are transmitted to signaling water stations. Indicator alarms are transmitted to handling stations and the alarm is activated. Water flows through all open sprinklers simultaneously. For prediction sprinkler systems, these are used in occupancies where preventing water damage is especially important. These are frequently used to protect computer rooms and to protect rooms and document storage areas. They combine deluge types of valves and fire detection devices. Pre-action system valves will not hold discharge into the sprinkler piping until it receives indication that a fire may exist.
Now let's talk about pre-action sprinkler systems. Piping is normally dry and can be used in freezing environments such as cold storage warehouses. Usually under low air pressure is maintained in the piping as supervisory function in the event of a leak or a break in the piping. Supervisory air pressure drops and transmits an alarm without admitting water to the system. Here you see a diagram of a pre-action sprinkler system, and you notice that there's a low air pressure alarm switch. So if that switch drops pressure below a certain point, water's not admitted into the closed sprinkler system. Operational sequence for pre-action sprinkler systems. The product of combustion detector senses presence of fire condition. The fire detection system sends a signal to the pre-action valve, causing the valve to open. Sensors in the piping system detect the flow of water into the system and trigger water flow fire alarm. When the level of heat at the sprinkler reaches an appropriate temperature, sprinkler fuses and water flows through the open orifice. All sprinkler systems' basic components include sprinklers, piping, valves, water supply source, and a fire department connection. Closed sprinklers are used in wet pipe systems, dry pipe systems, and pre-action systems. There are three main components of a closed sprinkler, and those are of interest to firefighters. They are a heat sensing device, deflector, and a discharge orifice. This slide shows automatic sprinkler system components. On the left, you see the components of a closed sprinkler. On the right, you see when heat sensing devices fall out, air and water escapes from the discharge orifice. You can see the water coming up through the center of the orifice. Open sprinklers are only used in deluge sprinkler systems. Heat sensing devices are located between the nozzle orifice and the deflector. This holds the plug over the sprinkler nozzle orifice. When heat sensing devices are subjected to enough heat to allow the plug to drop off, permitting air and or water to discharge from the sprinkler, then the sprinkler is then in action. A variety of heat sensing devices are used in sprinklers. You have fusible links, fusible alloy pellets, chemical pellets, and frangible glass bulbs. Operating temperatures vary from 135 plus to 575 degrees Fahrenheit plus, which is 57 to 302 Celsius. They are determined by maximum temperature and expected at the level of sprinkler under normal conditions. Under normal conditions, sprinkler with normal temperature rating of 165 degrees plus Fahrenheit or 74 degrees centigrade is most frequently used. If the ambient temperature exceeds 100 degrees Fahrenheit or 38 Celsius, the sprinkler with a higher temperature rating is used. Temperature ratings of sprinklers can be identified by color coding on sprinkler frame or frangible glass bulbs. The temperature rating is also stamped on the link in solder sprinklers. On other types of sprinklers, temperature rating is stamped on another part of the sprinkler. This slide shows you the automatic sprinkler system components. This is table 15.1 from your text, and it shows sprinkler temperature ratings, classifications, and color codings. These are all things that you should become familiar with. All sprinklers, except for deluge sprinklers, are thermal devices. There is inherent delay between the fire's ignition and the sprinkler's operation. This occurs as the thermal element's temperatures rise from room temperature to a melting/operating temperature. Now let's talk about response time index. This evaluates the relative speed of operation. The lower a sprinkler's relative or response time index, the faster it responds. To speed the operation of sprinklers, engineers have designed a quick response sprinkler. A deflector is attached to a sprinkler frame. It reshapes a solid stream of water that leaves the sprinkler orifice into a regular spray pattern. There are three basic types of sprinkler design: upright, pendant, and sidewall. Each of these designs have specific use and cannot be used interchangeably. Upright sprinklers are designed to deflect spray of water downward in a hemispherical pattern. Pendant sprinklers are used in locations where upright sprinklers would be impractical or unsightly. The deflector breaks the stream of water into a similar pattern or a circular pattern of small water droplets. Sidewall sprinklers discharge most of their water to one side. These are useful in such applications as corridors, offices, hotels, hotel rooms, and residential occupancies. The actual amount of water discharged by a sprinkler onto a fire is determined by the size of the discharge orifice, the pressure available at a sprinkler orifice, and the most common size of an orifice in an automatic sprinkler is 1/2 inch or 13 millimeters. Sprinklers are available with a wide array of other orifice sizes. This slide shows the amount of water being discharged from a given sprinkler, and it can be easily calculated. The equation 15.1 is in your book. So Q equals K times the square root of P, given that Q is the quantity of water discharged in gallons per minute, P is the discharge pressure at the sprinkler in PSI, and K is the discharge coefficient. Note, when using the formula with metric measurements, multiply the customary K factor by 1.44 before using the equation. The discharge coefficient, or K, varies with different sprinklers. It considers such factors as orifice diameter and smoothness. This is example 15.1 from your book. It determines the flow in gallons per minute from a 1/2 inch sprinkler with a K of 5.5 when the discharge pressure at the sprinkler orifice is 16 psi. So you take your formula Q equals K times the square root of P. And let's plug in the numbers. So Q equals 5.5 times the square root of 16. And when you work out the math, you get Q equals 5.5 times 4. So the Q is 22 gallons per minute. This is example 15.2 from your book. Let's determine the flow in gallons per minute from a 17 and 32nd inch sprinkler with a K of 8 when the discharge pressure at the sprinkler orifice is 16 psi. So the formula is the same, Q equals K times the square root of P. So we plug in the numbers. Q equals 8 times the square root of 16. Q equals 8 times 4. So the Q, or flow rate, is 32 gallons per minute. An increase in pressure means an increase in discharge for a given orifice diameter. Because sprinkler discharge varies with the square root of pressure, increase in pressure causes a smaller increase in flow than does an increase in the sprinkler orifice diameter. With sprinkler system piping, there are various NFPA standards that specify which types of piping are permissible in sprinkler systems. There are three basic types of pipe that are used: ferrous metal piping, copper piping, and plastic piping. Ferrous metal or black steel piping is most commonly used. The four types include Schedule 5, Schedule 10, Schedule 40, and Special Lightweight or XL. The primary disadvantage is that it will corrode and it's very heavy. Copper piping is highly resistant to corrosion and has low friction loss. It weighs less than steel pipe. It's neat in appearance where it's exposed. It's joined by soldering or brazing, used primarily where there's concern about corrosion damage to ferrous metal pipes. It is the most expensive of the three, however. Plastic piping. There are two types approved for wet pipe systems in light hazard and residential occupancies. Polybutylene, and the other is chlorinated polyvinyl chloride, also known as CPVC. In dry pipe systems, plastic pipe could be damaged before even discharging water. With plastic piping, it's the least expensive, lightest in weight, and it's easy to install, and it's joined together with plastic cement. However, it may not be installed in areas where ambient temperature exceeds 120 Fahrenheit, 49 Celsius for polybutylene pipes, or 150 degrees Fahrenheit or 66 degrees Celsius for CPVC pipes. Various types and sizes of pipes in sprinkler systems are given specific functional names. Water supply main comprises all piping below sprinkler valve. The riser is the vertical piping that extends up from the sprinkler valve to the first horizontal feed main. Feed mains are large pipes that supply water to each of the cross mains. The cross mains feed the branch lines. The branch lines are the pipes that contain the sprinklers. Every sprinkler system is equipped with a variety of water control valves, various operating, test, and drain valves. As far as control valves, they're used to shut off water supply to a system when replacing sprinklers or performing maintenance. They are located between the water supply source and the sprinkler system. They must always be returned to the open position after maintenance. Most valves are indicating valves, which allow personnel to visually determine whether or not they are open or closed. There are 4 types of indicating valves commonly used as sprinkler control valves. You have the outside stem and yoke, OS and Y valve, the post indicator valve, the wall post indicator valve, and an indicating butterfly valve. These are examples of each of these. On the left you see an OS and Y valve. On the right you see a post indicator valve. The bottom left is an indicating butterfly valve. And on the bottom right you see a wall post indicator valve. To ensure sprinkler control valves are kept open, they are chained or locked in the open position or electronically supervised. Operating valves serve as check valves, and these limit the flow of water to one direction to prevent recirculation or backflow of water. There are automatic drain valves that drain piping when pressure in the pipe is relieved to prevent pipe from freezing in cold weather. Globe valves are typically designed to be turned clockwise to open and counterclockwise to close. They have also stop or cock valves. These are used for drains and alarm testing. A globe type inspector's test valve is an operating valve, and you see a picture of one here. Every sprinkler system must have automatic water supply of adequate volume, pressure, and reliability. These sources of supply include municipal water systems, standby pumps connected to large static sources, elevated tanks or gravity tanks, and pressure tanks. The volume of water required to supply sprinkler system depends upon the occupancy classification. The water supply must be able to deliver the required volume of water at a residual pressure of 15 psi or 105 kilopascals at the highest sprinkler in the pipe scheduled design systems. In hydraulically calculated systems, the minimum residual pressure is 7 psi or 49 kilopascals. If water supply system cannot deliver these pressures, the fire pump must be added to the system. With municipal water mains, these are used most frequently. They tend to be the most reliable source of supply for sprinkler systems, but they must be of adequate pressure and volume. With elevated tanks or gravity tanks, these are one of the oldest methods used to supply on-site water for sprinkler systems. They provide a reliable source of water, and they must be placed on a tower or a platform many feet above the highest sprinklers. This is an example of an automatic sprinkler system component with water supply. You can see the water tank is 92 feet or 28 meters above the sprinkler system that it feeds. A fire pump at an above-ground reservoir provides large amounts of water without having to install a tower. It's used to protect where amounts of water may reach 250,000 gallons or 1,000,000 liters or more. It can draft from natural water sources. If a pump fails to start, no water will be supplied to the sprinkler system. If supplied from a natural source, it may not hold enough water during drought. Pressure tanks consist of large tanks of water and air under pressure. When the sprinkler system opens, air pressure in the tank forces water out of the tank and into the sprinkler piping. It's usually pressurized to 75 pounds per square inch or 525 kilopascals. It stores limited amount of water and has a limited discharge time. This is an example of a fire department connection. This enables the pumper to pump additional water into the system, boosting pressure and the volume of the water in the system. This is important in protecting buildings where primary water supply is weak or many sprinklers have opened. FDC or fire department connection is the most common type, and it consists of 4-inch or 100 millimeter pipe equipped with a Siamese fitting on the outside of a building. The check valve inside the building keeps the system water out of the portion of pipe extending outside the building. The automatic drain valve or ball drip valve is installed in the fire department connection to prevent problems associated with freezing temperatures. In single riser sprinkler systems, the fire department connection is attached on a sprinkler system side of the main supply valve. In multi-riser systems, the fire department connection or FDC enters the supply piping between the main supply valve and individual riser valves. This allows water to be supplied to the system when one riser valve has been closed. All fire department personnel must be familiar with the basics of sprinkler system operation and support and the particulars of specific sprinkler systems in their response district. There are 3 principal causes of unsatisfactory performance in sprinkler systems. You have a closed valve in the water supply or other part of the system, an inadequate water supply to the sprinkler system, or changes to the occupancy that negate the sprinkler system's effects. Each of these conditions can be identified relatively easily during fire inspection and/or pre-incident planning. The best time to identify and correct these situations is before an incident occurs. The most common cause of a closed valve is failure to turn the valves back on after maintenance work. In other cases, a system develops a leak and a valve is turned off. When performing inspections or pre-incident planning, check all valves to verify they are fully opened. The adequacy of water supply source should be established prior to construction of the building or installation of the sprinkler system. The common failure in sprinkler performance occurs when occupancy changes significantly, but sprinkler system is not updated to meet the needs of additional fire load. When performing pre-incident inspections, fire personnel should note the following details: construction, contents and layout of structure, and presence of sprinklers in all areas, the types of sprinkler systems in the building, and the water supply to the sprinkler system, and location and position of all water supply valves. The consequences of shutting off various valves in the system can be detrimental. With pre-incident inspection and planning procedures for sprinkler systems, location, condition of fire department connections, and sources of water to the supplement system that will not hinder the system operation is mandatory. Sources of water supply for other firefighting operations that will not jeopardize sprinkler system operation must be well known. Alternative means for supplying sprinkler system in the event of damage to the fire department connection must be known. Also, location of spare sprinklers and wrenches should be known, as well as location of water flow indicators and annunciator panels associated with the sprinkler system. When checking fire department connections, ensure that swivels operate properly, gaskets are in place in the intakes, and on new occupancies, verify the threads on the inlets are the same as those on the fire department hose. Information noted during pre-incident planning should be used to develop pre-incident tactical plans for structure and/or to strengthen the department's SOPs. Serious deficiencies should always be reported immediately to code enforcement personnel. Fire departments should develop effective pre-incident plans and SOPs for sprinklered occupancies long before being called to respond to those occupancies during an emergency. Most jurisdictions have an SOP requiring either first or second arriving pumper at the scene of sprinklered occupancy to be responsible for supporting water supply to the sprinkler system. Upon arriving at a scene, a sprinkler support engine company should proceed immediately to the fire department connection and make hose connections to the water supply source and the fire department connection. The pump operator should ensure intake hose connected to the hydrant will be large enough to pump the rated capacity of the fire pump. Also, upon arriving at scene, in most cases, the water supply source will be a fire hydrant in relatively close proximity to the fire department connection. If the water supply source is 200 feet or 60 meters or more from the fire department connection, or it is a static water supply source, that needs to be made aware of. So it may be necessary to reverse lay from the fire department connection to the water supply source. Water supply used for a sprinkler system should be separate from the water supply used for attack lines and master stream devices. Otherwise, water supply to a sprinkler system could be reduced to a point where it is ineffective. Do not use a static water supply source to boost pressure in a sprinkler system if possible, because debris could clog important parts of the sprinkler system. If the sprinkler system is connected to the municipal water supply system, untreated water might backflow into the municipal system and contaminate it. Backflow preventers and check valves can help prevent contamination. The pump operator should connect at least one 2.5-inch or 65 mm or larger hose between the apparatus discharge and the fire department connection. Hose lines between the water source and the pump and between the pump and the fire department connection should not be charged with water unless the IC directs it. Apparatus fire pumps should remain out of gear until the need to pump is confirmed. If the incident commander orders the pump operator to charge the sprinkler system through the fire department connection, the pump operator should place the pump in gear, open the water supply source, and begin discharging water into the fire department connection. Most fire departments use a rule of thumb of 150 psi or 1,050 kilopascals at FDC inlets as desired. FDC intake pressure. Supporting a sprinkler system in a high-rise building may require greater discharge pressure than a single standard fire department pumper can develop. Some cities that protect numerous high-rises have special high-rise pressure pumpers. These pumpers can supply water to the highest levels of high-rises with enough pressure and volume to properly support a sprinkler system. If the fire department does not have a high-pressure pumper, two pumpers connected together at the fire department connection may generate sufficient pressure. One pumper connects to the water supply source and pumps water into the intake of a second pumper connected to the FDC. The second pumper boosts pressure from the first pumper to much greater level than either pumper could create alone. These two pumpers together will pump 300 psi or 2,100 kilopascals into the FDC, and you can see the setup here as illustrated from the description in the previous slide. When the sprinkler system is adequately supported by the pumper, firefighters operating in proximity of flowing sprinkler should see an increase in pressure and a volume of water flowing through open sprinklers. Another way to observe the flow meter is if only a few sprinklers have been activated, flow may be very small. If no noticeable increase in sprinkler discharge occurs or the flow meter is showing no flow, there is most likely a closed valve. Sprinkler operation should not be discontinued until personnel near the fire have ensured the fire has been extinguished. If smoke is an issue, use standard ventilation practices. When firefighters have verified the fire is out, the IC can order the sprinkler system to be shut down. The pumper supplying the FDC stops pumping water into the system. Once outside water supply has been stopped, personnel can shut down flowing sprinklers. Pumpers assigned to the fire department connection should remain in place with hoses attached until salvage and overhaul operations are complete. Whether or not fire personnel restore the system, it is always good practice to have trained sprinkler system technicians inspect and service the system after it has been activated. NFPA Standard 13E, which is the recommended practice for fire department operation in properties protected by sprinkler and standpipe systems, recommends any post-incident report involving sprinkler system activation, including location of operating sprinklers, number of sprinklers that operated, the overall result of sprinkler operation, the perceived reason for any unsatisfactory operation, employee assigned to check the control valve, the engine company, if any, that supplied the FDC, and the size and number of hose lines connected to the FDC. It also requires the duration and pressure of water pumped into the fire department connection, any valves that were closed after the fire and who closed them, restoration functions, if any, performed by the fire department, the status of the system when the fire department left the scene, the operation of private water supplies used to supply the water sprinkler system, who was notified of the system activation, and the building representatives who were notified or contacted during the incident. Most pump operators' sprinkler support duties will involve connecting the pumper to the fire hydrant very close to the FDC for the sprinkler system, then pumping 150 psi or 1,050 kilopascals into the system. The process for determining pressure loss or pump discharge pressure can be used for more accurate required pressure. Most departments use a standard rule of thumb of 25 psi or 175 kilopascals to account for all pressure losses in sprinkler piping, friction loss in piping, pressure losses created by the fire department connection, and valves, bends, and fittings in the piping systems. When calculating pressure loss, other than rule of thumb system loss, the pump operator's primary concerns will be elevation loss in the system and friction loss in the hose lines between the pump and the fire department connection. Here's example 15.3 from your book. Determine the total pressure loss when a fire department pumper is supplying a fire department connection with two 3-inch hose lines with 2.5-inch couplings, each 50 feet long. 7 sprinklers are discharging 15 gallons per minute each on the 9th floor of the structure. Q is the number of sprinklers flowing, and GPM, gallons per minute per sprinkler. So if you extrapolate the math, Q is 7 times 15, so your Q or flow rate is 105 gallons per minute. For friction loss for the 3-inch line, you have your old friend CQ squared L. So friction loss for the 3-inch line equals 0.2, which is the coefficient from your table, times 105 divided by 100 squared, times 90 divided by 100. Note, the 3-inch lines are essentially Siamese lines, so C is taken from table 12.3, which is U.S. customary. So if we look at the math, we have the friction loss for the 3-inch line equals 0.2 times 1.05 squared times 0.5. And when we continue the math, the friction loss for the 3-inch line is 0.2 times 1.1025 times 0.5. So the friction loss for the 3-inch line is 0.1 psi. Now you have elevation pressure. That is 5 psi per floor times the number of floors minus 1. So your elevation pressure is 5 psi per floor, which is 9 minus 1. So the elevation pressure is 5 psi per floor times 8. So your elevation pressure is 40 psi. So your friction loss total equals the friction loss for the 3-inch hose plus the elevation pressure plus the system loss. And when you add in the math, you get friction loss total equals 0.1 plus 40 plus 25. So your friction loss total is 65.1 or 65 psi.
Here's an example 15.4 from your book. A fire department is pre-incident planning a new high-rise structure in their city. The department needs to determine the total pressure loss that will occur when 20 sprinklers with a 1/2-inch orifice and a K of 5.5 are all flowing water at 15 psi on the 18th floor of the structure. To supply the FDC, a pumper will have two reverse lines of 2.5-inch hose 300 feet to a fire hydrant and pump the lines. So you've got Q per sprinkler equals K times the square root of P. So let's add our math. Q per sprinkler is 5.5 times the square root of 15. And when we do the math, we get Q per sprinkler is 5.5 times 3.87. So the total flowing, or Q, is 21.3, which is 21 gallons per minute. The Q total for the number of sprinklers flowing, or the gallons per minute sprinkler, is Q total, which is 20 times 21. So your Q total is 420 gallons per minute. Now, friction loss for the 2.5-inch hose is our old friend CQ squared L. So we take friction loss for the 2.5-inch hose and we plug in the math. 0.5, which is our coefficient, 420 divided by 100 squared, and 300 divided by 100. Note the 2.5-inch lines are essentially Siamese lines, so C is taken from table 12.3, which is U.S. customary. That's our coefficient. So continuing, we take our friction loss for 2.5-inch line equals 0.5 times 4.2 squared times 3. And when we do all the math, we get friction loss for a 2.5-inch line at 0.5 times 17.64 times 3. And that comes out to friction loss for the 2.5-inch line at 26.5, which is rounded up to 27 psi. Now the elevation pressure is 5 psi per floor times the number of floors minus 1. So we have elevation pressure, which is 5 psi floor times 18 minus 1. So the elevation pressure is 5 psi per floor times 17. So our elevation pressure is 85 psi. So when we add everything together, we have friction loss total equals friction loss of the 2.5-inch line plus the elevation pressure plus the system loss. That gives us friction loss total equaling 27 plus 85 plus 25. We add those together. Our total friction loss is 132 psi. So let's look at example 15.5 from your book. Determine the required pump discharge pressure for the pumper in example 15.4. We take our PDP plus TPL plus NP. So we take our PDP equals 132 plus 15. So our PDP is 147 psi. Some review questions. First, describe the basic operational sequence for a wet pipe sprinkler system. That will be on page 465 of your manual. Next question, what is the primary difference between open sprinklers and closed sprinklers? That's on page 468 of your manual. Next question, what two factors determine the actual amount of water discharged by a sprinkler onto a fire? That's on page 470 of your manual. Next question, list one advantage and one disadvantage of the ferrous metal piping. That's on page 472 of your text. Next review question, describe the most common type of fire department sprinkler system connection. That will be on page 477 of your manual. Next question, what are the three principal causes of unsatisfactory performance in sprinkler systems? That will be on page 478 in your text. Next question. When should sprinkler operation be discontinued during an incident? That will be on page 482 of your manual. Now we're going to combine learning objectives 3 and 4. 3 will differentiate among the various types of standpipes, and 4 will calculate pressure loss and pump discharge for standpipe systems. Standpipe systems are an arrangement of pipings, valves, hose connections, and related equipment installed in a building with hose discharge connections. They're located to facilitate connecting attack lines for manual fire attack in remote parts of a building. They are most common in high-rise structures, but may also be found in large area one-story structures. They're required by code in high-rise buildings beyond the reach of fire department aerial ladders. Horizontal standpipes reduce effort required to advance hose lines long distances into a structure. In most high-rise buildings, the standpipe is the only means of manually controlling the fire on upper floors. Standpipe systems can be simple, where they consist of only a single vertical pipe or riser with a hose connection and an FDC. Complex can be consisting of multiple pumps and risers, valves, and reservoirs on upper floors. Standpipe systems are not acceptable substitutes for sprinkler systems, and sprinkler systems still provide the highest degree of protection in structure. The type of the system chosen for a building is dependent on many variables. First, the size of the building. Second, the atmospheric conditions to which the building will be subject. And third, the reliability of the building's water supply system as a whole. There are 5 types of standpipe systems recognized by NFPA Standard 14. You have dry automatic standpipes, wet automatic standpipes, semi-automatic standpipes, manual dry standpipes, and manual wet pipe standpipes. With standpipe system design, there are dry automatic standpipes. These operate much like dry pipe sprinkler systems. They may be used in locations where piping above dry pipe valve could be subjected to freezing. They have water supply that provides sufficient volume and pressure for operating hose lines without the need to boost pressure from an outside source. Firefighters will have to bleed off extraordinary amounts of air through the hoses before achieving a good fire stream. Wet automatic standpipes are the most commonly encountered design. They're very similar in design and concept to wet pipe sprinkler systems and are filled with water at all times. They can supply water in sufficient volume and pressure to establish effective attack lines anywhere in the protected occupancy. Semi-automatic standpipes are similar in design and operation to automatic dry standpipe systems. They require remote control activation devices in order to allow water into the piping system, and are capable of supplying water in sufficient volume and pressure to establish effective attack lines anywhere in protected occupancy. Manual dry standpipes do not have attached permanent water supply. They comprise a series of pipes, valves, and discharges that are empty when not in use, and they must be charged and supplied by fire department pumper attached to FDC. They require firefighters to bleed considerable amounts of air from the hoses before effective fire streams will flow from the nozzle or nozzles. Manual wet pipe standpipes are attached to small water supply source, and that source is only capable of keeping the piping system filled with water at all times. The fire department pumper will still have to charge the FDC in order for the system to be operated. The primary advantage over manual dry standpipe systems is that firefighters will not have to bleed as much air through the hose lines when charging system to fight the fire. The NFPA Standard 14 recognizes 3 classes of standpipe systems, Class 1, 2, and 3. Class 1 standpipe systems are primarily for use by firefighting personnel trained in handling large hand lines. They must be capable of supplying effective fire streams during more advanced stages of the fire within the building for fighting fire in the adjacent building. And they have a 2.5 inch or 65 millimeter hose connection attached to the standpipe riser. This is a Class 1 standpipe connection. NFPA 14 requires Class 1 standpipes in high-rise buildings to be automatic and semi-automatic. Buildings that are not high-rises may have manual, semi-automatic, or automatic Class 1 systems. In buildings equipped with single Class 1 standpipe systems, the system must be capable of flowing 500 gallons per minute or 2,000 liters per minute at 175 psi or 1225 kilopascals through the most remote hydraulically challenging discharge. If the building is equipped with more than one Class 1 standpipe, each additional standpipe must be capable of flowing 250 gallons per minute or 1,000 liters per minute. The maximum flow required for any level in a building is 1,000 gallons per minute or 4,000 liters per minute. A Class 2 standpipe system is designed for use primarily by building occupants who have little or no training in firefighting. It may be used by firefighters during initial fire attack or in mop-up operations. That must have a hose station located at hose connections. This is an example of a Class 2 standpipe hose cabinet, and on the right you see a Class 2 standpipe hose reel. Fire department personnel should not use supplied hose and nozzle for fire attacks. They should carry their own hose packs into the structure. Disconnect the hose line and then connect their own equipment. For Class 2 systems, they must be capable of supplying 100 gallons per minute or 400 liters per minute at 100 psi or 700 kilopascals to the most remote hydraulically challenging discharge on the system. The requirements do not change if multiple systems are located in the building. They cannot be depended on for fire control operations. NFPA Standard 14 states that Class 2 standpipes shall not be required in buildings fully protected by a sprinkler system. The building should have Class 1 standpipe system, and the 2.5-inch or 65 millimeter caps on the standpipe discharges must be equipped with 1.5-inch or 38 millimeter reducers and chained caps. NFPA Standard 14 requires both Class 2 and Class 3 systems to be wet systems unless they are in facilities subject to freezing conditions, and have a fire brigade personnel trained to operate the system until the fire department arrives. Class 3 standpipe system combine features of Class 1 and Class 2 systems. They have both connections for fire department personnel and hose stations and connections for use by building occupants. They must allow Class 1 and Class 2 services to be used simultaneously. The minimum required flow rates are the same for those as Class 1 standpipes. All standpipes are required to use ferrous metal, steel, and copper piping. The piping must be capable of withstanding operating pressures of up to 300 pounds per square inch or 2,100 kilopascals, protected from mechanical damage, located in exit stairways, or protected to the same degree as exit stairways. Various types of Class 3 hose cabinets and connections are what you see illustrated here. Class 1 and Class 3 standpipe risers that are standalone systems must be at least 4 inches or 100 millimeters in diameter, and combined with a sprinkler system that must be at least 6 inches or 150 millimeters in diameter. Horizontal branch lines that extend to discharge on individual floors must be at least 2.5 inches or 65 millimeters in diameter. Now let's talk about standpipe system components, those being hose connections. Hose connections on standpipes for attack lines must be no less than 3 feet or 1 meter and no more than 5 feet or 1.5 meters from the floor on which they are located. All discharges should be equipped with the same hose threads that local fire departments use. Class 1 standpipes must be equipped with 2.5-inch or 65mm hose connections at the following locations. First, each intermediate landing between floor levels in every required exit stairway. Second, on each side of the wall adjacent to exit openings of horizontal exits. Third, in each exit passageway at the entrance from the building areas into the passageway. Next, at entrance to each exit passageway and corridor in covered malls, and at the interior side of public entrance from the exterior to the mall, and at the highest landing of stairways with stairway access to the roof on the roof where stairways do not access the roof. The travel distance to any point on the floor protected by a Class 1 standpipe system shall not exceed 150 feet or 45 meters in unsprinklered occupancies, or 200 feet or 60 millimeters or 60 meters in sprinklered occupancies. Class 2 discharges and hose cabinets should be located so travel distance on any part of the floor is no more than 130 feet or 40 meters for cabinets equipped with 1.5-inch or 38mm hose, or 120 feet or 37 meters for cabinets equipped with hose smaller than 1.5-inch or 38mm. If a building is sprinklered, a 2.5-inch or 65mm hose connection should be outfitted with a 1.5-inch or 38mm reducer and cap. And you see that illustrated right here. Class 3 systems have hose connections that meet requirements for both Class 1 and Class 2 systems. NFPA Standard 14 requires pressure regulating device to limit discharge to these pressures unless otherwise approved by the fire department. 100 psi or 700 kilopascals for a 1.5-inch or 38mm discharge, or 175 psi or 1225 kilopascals for a 2.5-inch or 65mm discharge. With pressure regulating devices, these prevent pressures that make hose difficult or dangerous to handle. They also enhance system reliability and may improve system economy by eliminating the need for booster pumps. There are types of pressure regulating devices. One type consists of simple restricting orifice that's inserted in the waterway. Another type may consist of vanes in the waterway that can be rotated to change cross-sectional areas through which water flows. Standpipe system components, pressure regulating devices, we're going to discuss now. First, pressure regulating device must be specified and adjusted to meet a pressure flow requirement of an individual installation. Next, pre-incident planning and inspection procedures must focus on the presence of pressure regulating devices and their proper operation. Third, if not correctly installed and properly adjusted, it may greatly reduce available flow and seriously impair firefighting capabilities. And fourth, each Class 1 or Class 3 standpipe system requires one or more fire department connections through which the pumper can supply water into the system. Standpipe system components. This is an example of a high-rise building with 2 or more zones. This requires a fire department connection for each zone. For standpipe system zones beyond 450 feet or 135 meters, a fire department connection is not of any value unless the fire department is equipped with special high-pressure pumpers. NFPA Standard 14 specifies there shall be no shutoff valve between the fire department connection and the standpipe riser. In multiple riser systems, gate valves are provided at the base of individual risers. Hose connections to FDCs must be female, equipped with standard caps, and hose coupling threads should conform to those used by the local fire department. In some situations, fire department connections must be designated by raised red letter signs on the plate or fitting reading Standpipe. If the FDC does not service all of the building, the sign must indicate which floors are serviced. You see illustrations of that right here on this slide. Pre-incident inspection and planning procedures for standpipe systems should start before building construction begins. A detailed design plan should be submitted to the local fire department or building department in accordance with local codes. In a high-rise building, a standpipe will have to be in partial operation as construction proceeds. When installation is complete, following tests and inspections should be performed. First, the system should be hydrostatically tested at a pressure of at least 200 psi or 1400 kilopascals for 2 hours to ensure tightness and integrity. And second, the system should be flow tested to remove any construction debris to ensure there are no obstructions in the lines. On systems equipped with automatic fire pumps, a flow test should be performed at the highest outlet. A fire pump should be tested to ensure it will deliver its rated flow and pressure, and all devices used should be inspected. Hose stations and connections should be checked to verify they are in cases within 6 feet or 2 meters of the floor and positioned so the hose can be attached to the valve without kinking. Each hose cabinet and closet should be inspected for conspicuous signs that read fire hose and or fire hose for use by occupants of building. FDCs should be checked for proper fire department thread and for sign indicating standpipe with a list of floors served by that connection. When a dry standpipe is used, check for a sign indicating dry standpipe for fire department use only. To avoid potential liability, fire department personnel should not perform actual tests. Fire protection contractor or buildings operating staff should carry out the actual testing of standpipes. Fire department personnel should be on hand, however, to witness the tests. After the initial inspection, testing, approval, standpipe systems need to be inspected and then tested at regular intervals. All companies expected to operate in occupancy should make pre-incident planning trips to examine the system and note the following items to include in SOPs. First, all water supply valves are sealed in the open position. Second, power is available to the fire pump if so equipped. Third, individual hose valves are free of paint, corrosion, and other impediments. And fourth, hose discharge threads are not damaged and caps are present. Also, what should be checked are that hose discharge valve wheels are present and not damaged. Hose cabinets are accessible. Hose in Class 2 and Class 3 hose cabinets is in good condition, has proper dryness, and is properly positioned. Next, discharge outlets in dry systems should be closed. Dry standpipe is drained of moisture, and access to the fire department connection is not blocked. Also, it should be checked that the FDC is free of obstruction, swivels rotate freely, and caps are in place. Water supply tanks are at proper level. Next, if equipped with high or pressure regulating devices, these devices are tested as required by the manufacturer. Next, hose valves on dry systems are closed. Then pump discharge pressures that will be required to the supply system are determined, and dry systems are hydrostatically tested every 5 years. At fire department operations with occupancies equipped with standpipes, SOPs for operating at occupancies equipped with standpipes should address at least the following. First, equipment to be carried into the structure by companies that will hook attack lines to standpipes. Second, pump discharge pressure that pumpers assigned to supply FDC will need to use. And third, how to identify which standpipe if the building has more than one, will be used for firefighting operations, so pumper connects to the correct FDC. Also, methods for flaking out hose between standpipe hose connection and entrance to the fire floor should be checked. Procedures for adjusting pressure, reducing devices if that becomes necessary, and methods for bypassing FDC to supply system in the event that the FDC is blocked or otherwise inoperable. Fire personnel should always carry their own hose and equipment into the structure for use with the standpipe system. Never rely on the hose in the structure's hose cabinets. High-rise packs, bundles, or all carts contain all items necessary to place the standpipe attack line into service. Before leaving the lobby, review the building floor plan if available, the type of standpipe. Extra hose, air cylinders should be brought into the building and kept in the lobby until needed, and personnel should be assigned to check riser valves and fire pump operations. Proceed to the floor below the fire in protective clothing and SCBA. Walking up the stairs is safest. Connect the hose to the standpipe on the floor below the fire and advance the hose up to the fire floor. Note, one firefighter must remain at the standpipe valve to charge the line after it's been moved into the operating position. When heavy fire is developed on a fire floor, the line should be charged and the stairwell door carefully opened to begin the attack. Additional hose lines can be attached to hose valves on lower floors and advanced to the fire floor. Firefighting operating standpipe valves should watch for fire developing behind the attack team and warn them, and decide in advance what type of nozzle to use. With fog nozzles, they produce fine water droplets that afford better protection to advancing firefighters and provide more efficient heat absorption. If scale is present in the standpipe, it may obstruct the fog nozzle. Although the solid stream does not produce spray, it provides good reach, penetration into burning debris. When a building has multiple standpipes, firefighters can use more than one riser for a multiple line attack. Firefighters advancing onto the floor from different directions must keep in contact by radio. The fire department can use a number of simple operations to overcome standpipe impairments. If the FDC has a frozen swivel, a double male can be used with a double female. If the FDC is totally unusable, a standpipe riser can be charged at the first floor level by attaching a double female to the hose valve at the first floor level. If the individual hose valve on the upper floor is inoperative, the valve on the next floor down can be used. Also, to overcome the problem in single riser building where the standpipe is totally unserviceable, firefighters may have to hoist line up outside the building. Standpipes in adjacent buildings can also be used to protect exposures. And as a last resort, supply hose can be laid up an interior stairwell to take the place of standpipe. If aerial apparatus can reach the fire floor, standpipe connections at the tip of an aerial apparatus can supply hose lines on upper levels. So let's talk about aerial device standpipe connections. If a fire floor is higher than the reach of an aerial device, it can be used in place of hose lines for the first 6 to 10 floors. An aerial device will have much less friction loss than would hose used for the same distance. Once an aerial device is used to supply hose line, it is essentially out of service. Many fire departments choose not to use them to supply attack lines in structures. Hose valves in dry standpipes may be open and left in that position, and personnel should check that all standpipe valves as they first proceed up stairwells. If the standpipe FDC is not properly supported, firefighters in that area will be in peril. All pump operators must be thoroughly knowledgeable about SOPs related to standpipe support and follow them explicitly. To ensure each system is supported properly, the required pump discharge pressure must be calculated individually. Friction loss in standpipe is small unless flows are large, so allowance must also be made for pressure losses in FDC and pipe bends. Calculate straight 25 psi or 175 kilopascals loss to account for friction loss in the standpipe system. When a standpipe system is known to be equipped with pressure-reducing valves, the elevation pressure must be based on the total height of the standpipe or the zone being used. The pressure-reducing valve generally acts to reduce whatever pressure is presented to it. If the pressure at the pressure-reducing valve is less than that for which the valve was adjusted, pressure for hose lines will be inadequate. According to NFPA Standard 14, at no time should standpipe system be pressurized in excess of 200 psi or 1400 kilopascals unless designed for higher pressures. When determining correct pressure to charge the standpipe system, consider the following factors: friction loss in hose between the pumper and the fire department connection, friction loss in the standpipe system, pressure loss due to elevation, number, size, and length of attack lines connected to the standpipe, and required nozzle pressure. For handline fog nozzles, they typically operate at 100 psi or 700 kilopascals nozzle pressure. Exceptions to this are special low pressure nozzles. With solid stream handline nozzles, they should be operated at discharge pressures of 50 psi or 350 kilopascals. So let's look at hydraulic calculations for pump operators supplying standpipe systems. This is example 15.7 from your book. A fire is discovered on the 8th floor of a structure. Firefighters from the first arriving engine company proceed to the 7th floor of the occupancy and connect 3 50-foot sections of 2.5-inch hose to the standpipe outlet. The hose is equipped with a solid stream nozzle that has a 1.25-inch tip. The pump operator connects the pumper to a fire hydrant and stretches 2 lines of 3-inch hose, each 100 feet long, with 2.5-inch couplings to the fire department connection. What is the total pressure loss between the pumper connected to the FDC and the nozzle on the attack line? Well, you're going to use a familiar formula. Gallons per minute equals 29.7 times the diameter squared times the square root of the nozzle pressure. So let's do the math. Gallons per minute equals 29.7, which is your coefficient from your table in your book, times 1.25 squared times the square root of 50. When you calculate the math out, you get GPM equals 29.7 times 1.5625 times 7.07. So your GPM is 328 gallons per minute. Now let's look at the friction loss in the 2.5-inch attack line. That uses our formula CQ squared L. So our friction loss for the 2.5-inch attack line, let's plug in the numbers, is 2, which is our coefficient, 328 divided by 100 squared, and 150 divided by 100. If we do the math, our friction loss for the 2.5-inch attack line is 2 times 3.28 squared times 1.5. And when we do the math, we come up with friction loss for the 2.5-inch attack line equaling 2 times 10.76 times 1.5. And that gives us a total of friction loss on the 2.5-inch attack line at 32.3, and we round to 32 psi. Now we have to look at elevation pressure. Elevation pressure is 5 psi per floor times number of floors minus 1. So the elevation pressure is 5, and we have an 8-story building, and we subtract 1 floor. So our elevation pressure is 5 times 7. So our elevation pressure is 35 psi. Now our friction loss for the 3-inch line is the same formula we used for the 2.5-inch line, which is CQ squared L. So the friction loss for the 3-inch attack line, when we add in the numbers or plug in the numbers, is 0.2, which is our coefficient, times 328 over 100 squared times 100 divided by 100. And when we do the math, we come up with friction loss on a 3-inch line equals 0.2 times 3.28 squared times 1. And when we calculate that out, the friction loss for the 3-inch line is 0.2 times 10.76 times 1. So our friction loss for a 3-inch line is 2.1, which is 2 psi. So to figure it out, our TPL equals friction loss of 2.5-inch attack line plus elevation pressure plus friction loss for the 3-inch line plus system loss. When we plug in all those numbers, our TPL is 32 plus 35 plus 2 plus 25, so our TPL is 94 psi. Some review questions for you. First, describe the differences between sprinkler systems and standpipe systems. That will be on page 490 in your manual for answer. Next question, list the 5 types of standpipe systems. That will be on page 491 in your manual for answer. Next question, what is the exception of the NFPA requirement of class 2 and 3 standpipes when they are subject to freezing temperatures? That will be on page 494 of your text. Next question, what is the maximum distance allowed for hose connections from the floor when they are located to standpipe attack lines? That is on page 495 for the answer. Next question, list at least 3 considerations that should be addressed in fire department operation SOPs. That will be on page 500 in your manual for the answer. And next question, why is supplying water at the correct pressure more important for standpipe fire department connections than for sprinkler fire department connections? That will be on page 504 for answer. Class, thank you for all of your time and attention in this class. It's a complicated class. There's nothing terribly complex in this particular chapter. However, as always, if you have any questions, please make sure to contact your instructor. Thank you so much for your time and attention in this course. We really appreciate it. Thank you so much.